Hi there, and welcome to this lesson. In this lesson, we'll be learning about equations of motion, okay? And on the equations of motion, we'll be learning about acceleration due to free fall. Okay, so in the last lesson, we learned about uniform acceleration, linear motion, basically. But in this lesson, we'll be learning about acceleration due to free fall. Now, as the lesson progresses, anything you don't understand, be sure to get across to your tutor, who would be more than happy to help. And yes, let's jump right into the lesson. So, acceleration due to free fall. Now, what exactly is this about? Now, a body is said to be in free fall when it is released from a given height, okay? And it accelerates towards the Earth's surface under the influence of gravity. So basically, you have just dropping something from a given height and having it accelerate towards the Earth's surface. Now, basically, when you drop something, there's something we call gravitational acceleration, okay? And then what it is the force of gravity tends to draw bodies to the Earth's surface. So if you throw anything up, it comes back down. All right. And then what it is, or if you drop something from a particular height, it accelerates downwards, and that acceleration is gravitational acceleration, and gravitational acceleration is constant, is 9.8 meters per second squared. Okay, so the acceleration the acceleration of a body in free fall is always 9.8 meters per second squared. And what it is basically you have a given height, and you have this body, and basically you're looking to drop this body. Now if you drop this item, if you drop this object, um its initial velocity is zero, okay, because you're just dropping it. You're not applying any force, you're just dropping it. So it starts from rest and starts falling, starts accelerating towards the Earth's surface, okay. And then what it is, acceleration is gravitational acceleration, that's 9.8 meters per second squared, and it will accelerate up until the point of impact when it gets to the surface of the Earth, and just before impact it would have attained a final velocity v. Okay, so just like you have a typical body that's moving on the Earth's surface, accelerating on the Earth's surface, maybe you have a car that's accelerating, initial velocity zero from rest, and as accelerating the velocity increases, it's really no different. The one difference being in this case that the acceleration of a body in free fall is always 9.8 meters per second squared. So just like you have for any accelerating body, acceleration in free fall also conform to the different equations of motion. Okay, so we have and basically we do this, all of this happen over a given span of time. So the different equations of motion, we start off with v equals u plus at. Basically we have this from v minus u, a equals v minus u over t, and we will just change the subject formula. We have v equals u plus at, and now in free fall u is 0, okay, and then a is gt. So what we have is we have v equals gt. Simple. Okay, so v equals the final velocity, the velocity of the body just before it hits the ground, is gravitational acceleration by the time taken for the fall. So we also have s equals ut plus half at squared. Okay, now the distance is always the vertical height, okay, because the body travels through a vertical height. So the distance or the displacement of the body s is always h. U, like we said, is 0, a is g, and we have t squared. So if we bring all of that together, what we have is we have h replacing s equals ut is 0, okay, equals half gt squared. So h equals half gt squared. And then finally we have v squared equals u squared plus 2as. V squared equals 2gh. Simple, straightforward. Now that's pretty much all you need to know for this lesson. But there's something very, very important that it'd be nice for us to touch on this before we proceed. And it's something interesting about comparing two bodies in free fall. Okay. Now, um, we have this vertical height, and what we're going to do is we're going to drop a stone and a feather. Okay, so a stone and a feather. I'm going to drop them from the same height. Now, if you do this in real life, basically, the stone will hit the ground before the feather. But in truth, two bodies, because basically I've been talking to you about acceleration due to free fall, final velocity. We've not mentioned anything about weight, okay? And basically, the weight has nothing to do with, in truth, has nothing to do with the acceleration of the body or the time it will take for the body to hit the ground. In truth, without considering air resistance, two bodies in free fall will accelerate at the same pace towards the Earth's surface. Now, here's what it is. It's the air that makes a difference, okay? And that is why in real life the stone hits the floor before the feather. But if you actually suspended this two in a vacuum where there's no air, okay, and you will basically only force acting on those two bodies would be the force of gravity, because air brings in a different force, a force air resistance. Okay, but then if you have a vacuum is a space without air. A vacuum is a space without nothing, without air. And basically, you suspend these two bodies and you drop them in a vacuum with the only force acting on these two bodies is the force of gravity. I tell you, they will drop at the same time. So what it is you have the weight of this body pushing this, bringing these bodies down. Okay, so gravity bringing these bodies down, and then you have a different force acting upwards, and this is air resistance. Okay, and what you actually have is the actual acceleration of this body downwards is the resultant of these two forces. We haven't talked about resultant forces, but basically, after you actually need to subtract the resistance from the weight, and then you have the resultant force acting on this body as a result of gravity, and which would then determine the acceleration with which its bodies will accelerate towards the surface of the earth. And what it is that because the stone is heavier than the feather, um, the stone would overcome air resistance better. Okay, so basically you still have a large resultant force in the end. What you have is you have the stone accelerating faster than the feather, and that is why the stone will get to the earth's surface before the feather. But without considering air resistance, okay, we're still talking about kinematics. We're not talking about forces yet. So basically, without considering air resistance, all of these equations apply. Okay, and in truth, if you suspend two bodies regardless of their weight, regardless of any forces, you would have both of them hit the ground at the exact same time. Okay, now let's do some examples. We have example one. And example one, we have Kyle dropped a penny from the top of a tower and it took 1.85 seconds to hit the ground. Now calculate the velocity at impact in meters per second. Okay, so we have Kyle, and Kyle dropped a penny from the top of a tower. It took 1.85 seconds to hit the ground. Calculate the velocity on impact. This is very simple. So we have V equals gt. What we have here is we have time. Again, we're looking to find the final velocity, the velocity before impact. So we just multiply gravitational acceleration by time. And what we have in the end is we have 18.13 meters per second. Simple, straightforward. Let's do another example. Now, example two. In example 2, we have an object falls from a high building and hits the ground in 9 seconds. Now, ignoring air resistance, what is the distance that it fell and how long did it take the object to fall 200 meters? Now, basically, we have time and we're looking to find height. Okay, and the formula that relates to displacement and time is always S equals ut plus half at squared, or in free fall form, h equals half gt squared. And what we have is we have g is 9.8 meters per second squared, and t in this case is 9 seconds. So we have this body falling in 9 seconds, and we're looking to find the height through which this body fell. So quite simply, we just do that, and we have 396.9 meters. Simple, straightforward. Now, We're also given a case where we're looking to find the time it took for this body to fall through 200 meters. So this body was falling, the total height, as we found from step one, was 396 meters. Okay, and we're looking to find the time it took this body to fall through just about half that. Okay, at 200 meters. And to do that, we have T equals 2h over g, root of 2h over g. And then basically, you have that when you rearrange that formula there. And what you have is you have g is 9.8 meters per second squared and h as 200 meters. And then you just go ahead and put your values in, and you should end with 6.39 seconds. Simple, straightforward. Example 3, we have a man is standing on the edge of a 20-meter high cliff and he throws a rock vertically with an initial velocity of 10 meters per second. Now, how high does the rock go? Now, we've been talking about bodies in free fall, okay, and basic bodies accelerating in free fall. But what we have here actually, first of all, ignore the first bit. It doesn't matter that the young man is standing on a cliff. Okay, he could be standing anywhere and throw a rock upwards. Standing on a cliff doesn't make any difference at all. But what it is he threw the rock upwards with an initial velocity of 10 meters per second, and we're looking to find how high the rock will go. So we're looking to find height. Now, we know about bodies falling from height down, okay, but we don't know much about, but at this point, we don't know much about bodies going from down up. And I just tell you, it's pretty much the same thing. The only difference is the body moving upwards with decelerate. So it pretty much just goes in reverse. So you know, body falling down starts from zero meters per second, and then attains the final velocity just before hitting the ground. A body going up goes up with an initial velocity, which would be that final velocity, and it goes up till it reaches the final velocity of 0 before it starts coming back down. Okay, so it's pretty much the same thing, but as opposed to accelerating, we have deceleration in this case. Okay, and what it is if you consider this formula, v squared equals u squared plus 2as. Okay, and in this case, because we're going in reverse, we have 0 equals u squared minus 2gh. And the reason for that, the reason we have minus 2gh is that g is negative because it's deceleration. Okay, so the acceleration in this case is negative, and when you work that, what you have in the end is you have h squared equals h equals u squared over 2g, and we have our u as 10 meters per second, g as 9.8 meters per second squared. We'll just use that to find our h, and we should end up with 5.1 meters. So like I said, basically, it really doesn't matter where the young man was standing. He could have been standing at 0 meters from the ground, and it won't matter how long it would take for, or how high the rock goes, or basically that's what it is. Or the one difference you can say is it went 25 meters from the Earth's surface, but basically you know that it traveled through 5.1 meters. And yeah, that would bring us to the end of this wonderful, very interesting lesson. You can go ahead now and attempt questions on the worksheet. Bye for now.